Hello everyone. In this video, we will learn to understand and label various parts of a heating curve, to use the enthalpy of fusion and vaporization to calculate heat absorbed or released during a phase change. In general, substances can exist in three phases based on the temperature and pressure: solids, liquids, and gases. If we take any solid and heat it, it melts to form a liquid. We call this process melting or fusion. And if you continue heating, the liquid boils to form a gas. We call this process vaporization. Conversely, if we take any gas and cool it or remove heat from it, the gas changes its phase to liquid. This process is called as condensation. And if we continue to cool the substance, the liquid changes to solid, and we call this process freezing. Sometimes solids can directly transition to a gas phase, which is called as sublimation. An example of sublimation is solid carbon dioxide subliming into gaseous carbon dioxide at room temperatures. Gases can directly transition to solid phase as well. This process is referred to as deposition. As we move from solids towards the gases, the overall energy content of the substance increases as heat is being added to the system. Conversely, when we move from gases towards solids, the overall energy content of the substance decreases as we are taking away heat from the substance. We can represent this entire process and the energy changes associated with the process by plotting a heating curve. Heating curve is a plot of the amount of heat added to a substance on the x-axis and the temperature of the substance on the y-axis. Before going any further, I want to restate that the temperature of a substance is a measure of average kinetic energy of all the particles in that substance. That is, as the temperature increases, the average kinetic energy of the particles increases. Let us now draw the heating curve for water. Let us say we just took some ice out of the freezer and placed it inside a beaker. The temperature of the ice is at -100 degrees Celsius. And we slowly add heat to ice by placing the beaker on a Bunsen burner. As the heat goes into the ice, we notice that the temperature of the ice increases. If we plot the amount of heat added on the x-axis and the temperature of the ice on the y-axis, we will notice that the temperature of the ice increases linearly with the amount of heat added. As we discussed earlier, the temperature of a substance is a measure of average kinetic energy of all the particles in the substance, which means as the temperature of the ice increases, the average kinetic energy of all the particles in the ice increases as well. During this time, the heat flows into the ice and the random vibrations of water molecules inside the ice keeps increasing, which increases the average kinetic energy of the ice. This increase in temperature continues until the temperature of ice reaches 0 degrees Celsius, at which point the water molecules vibrating in the crystal lattice break out of their fixed lattice position and melts into liquid water. During this phase transition from ice to water, the heat continues to go into the system, but the temperature of the system doesn't increase. That is, the average kinetic energy of the system does not change. So, what is happening to the heat that is absorbed by the system? The heat that is added is utilized to break the hydrogen bonds between the water molecules in the solid ice and convert them into liquid water. That is, the heat added results in the increase of potential energy, not the kinetic energy of the system. Since the average kinetic energy of the system does not change during a phase transition, we don't see any change in the temperature. This temperature at which a solid melts into liquid is called as melting point. And for water, the melting point at 1 atm pressure is 0 degrees Celsius. Now, once all the ice is changed into water, the temperature of water again starts to linearly increase with the heat added. During this time, the random motion of water molecules increases, therefore increasing the average kinetic energy and the temperature of water. This increase in temperature of the water continues until the temperature of the water reaches 100 degrees Celsius. At this point, the liquid water changes into gaseous water vapor. During this phase transition, the temperature of the liquid-gas mixture remains constant as the heat is being added into the system. The heat that is going into the liquid water mixture is used to convert the liquid water into water vapor without increasing the average kinetic energy of the mixture. During this time, the potential energy of the system goes up. The temperature at which the liquid water changes to water vapor is called as boiling point. And for water, the boiling point at atmospheric pressure of 1 atm is 100 degrees Celsius. Now, once all the liquid water is changed to vapor, the temperature of the water vapor again starts to increase linearly with heat added. So, if you look at the heating curve, we need some heat to convert the solid ice at 0 degrees Celsius to liquid water. This is called as enthalpy of fusion or heat of fusion. Similarly, we also need heat to convert liquid water at 100 degrees Celsius to water vapor at 100 degrees Celsius. And the heat required to convert all the water at 100 degrees Celsius to water vapor at 100 degrees Celsius is called as heat of vaporization or enthalpy of vaporization. So, let us now define what enthalpy of fusion and vaporization is. The heat energy required to convert 1 mole of solid to liquid at its melting point is called as enthalpy of fusion. And we represent enthalpy of fusion as delta H FUS. And the units that we use to express enthalpy of fusion are kilojoules per mole of substance. Enthalpy of fusion is a positive number because during this phase transition from solid to liquid, heat flows into the system. For example, 1 mole of solid ice converted into 1 mole of liquid water, enthalpy of fusion for this reaction is 6.02 kilojoules per mole at 0 degrees Celsius. Similarly, the heat energy required to convert 1 mole of liquid to gas at its boiling point is called as enthalpy of vaporization, delta H VAP. Again, we use same units of kilojoules per mole. For example, if we take 1 mole of liquid water and add heat to convert it into 1 mole of water vapor, the enthalpy cost, which is delta H vaporization, there is a mistake here, it is delta H VAP, is 40.7 kilojoules per mole at 100 degrees Celsius. For any substance, usually the delta H vaporization, that is enthalpy of vaporization, will be much higher than enthalpy of fusion. That is to say, it takes more heat to convert from a liquid to gas than to convert from solid to liquid.